In this series of videos, we're going to consider two types of improper integrals. Type 1 looks like the integral from negative infinity to a of f of x dx, or the integral from a to infinity of f of x dx. Type 2 is the integral from a to b of f of x dx, where there exists a c in the interval from a to b, could be at an endpoint or interior, such that the limit as x approaches c is equal to infinity or negative infinity. The first type we can characterize as being an infinite interval. For the second type, we can characterize the situation as having an infinite discontinuity, otherwise known as a vertical asymptote. In all of these cases, we find the value of the integral, if it exists, by taking limits. If the limit exists as a finite number, then the integral is said to be convergent. If it does not, and that means it either does not converge to a number or the answer is infinity, then it is divergent. And then as a note here, the type 1 improper integral can span the x-axis. That is to say, it could be an integral from negative infinity to infinity of f of x dx, in which case we would express it as the integral from negative infinity to c of f of x dx plus the integral from c to infinity of f of x dx, provided that both integrals on the right-hand side are convergent. And in this situation, c can be any real number. And just like when you first saw integrals, if the function is at least 0 over the interval in question, then the integral can be interpreted as an area. Let's see what this looks like. We are going to look at the integral from 1 to infinity of e to the negative 1 over x divided by x squared dx. In particular, what we're going to do is determine whether the integral is convergent or divergent, and if it is convergent, we're going to evaluate it. The first thing we do is, well, folks, I have some sad news for you. We actually cannot compute this integral from 1 to infinity. Cannot do it. Nope, not at all. So the very first thing we have to do is we have to turn this into a limit. We're going to take the limit as t approaches infinity of the integral from 1 to t of e to the negative 1 over x divided by x squared dx. Now we can do it. You see, I can have limits that go from 1 to t, no big deal, and then I'll let t go to infinity. But if the integral starts out with a limit that is infinity, can't do it at all. And I'm emphasizing that because people blow past that first step. If you see an improper integral, your very first step has to be to write a limit. If that's not your first step, I'm sorry to say you're not getting full credit. I don't even think I can say I'm sorry to say that. It's just a fact that you won't be getting full credit. Now, if we look at the integrand, e to the negative 1 over x divided by x squared, I'm thinking substitution. If we let u equal negative 1 over x, then du is 1 over x squared dx. We are basically looking at the integral of e to the u du. I'm not going to make a substitution here because we already have enough going on with the limit as t goes to infinity. But we can say that this evaluates to the limit as t approaches infinity of e to the negative 1 over x, and the limits are from 1 to t. The substituting goes the way you would think it would. It's the limit as t approaches infinity of e to the negative 1 over t minus e to the negative 1. At this point, you may notice I don't have parentheses around the two-term result of evaluating at the limit, or at the end, the limits of integration, excuse me. That's because we're looking as t approaches infinity, and t is only evident in the first term. It would not be incorrect to wrap e to the negative 1 over t minus e to the negative 1 in parentheses. I'm just not going to do it. Well, as t approaches infinity and t appears in a denominator with a numerator of 1, that exponent is going to go to 0. And so taking the limit, we're going to get 1 for the first term and then minus, and I'll go ahead and write it as 1 over e, and we have a finite value. Since it's a finite number, we're going to say this is convergent. Now I'd like for you to do the next one. It's the integral from 0 to infinity of the sine of theta times e to the cosine of theta d theta. See what you can do with this. Pause the video, come back when you're done, or if you get stuck. Looking at the integrand, I see an e to the cosine of theta. I'm going to call that u, so du is negative sine of theta d theta. Multiplying and dividing by a negative 1 is going to give me a du, and because the upper limit was infinity, we need to take the limit as t approaches infinity of the integral from 0 to t of now negative sine of theta times the e to the cosine of theta d theta, and there's a minus sign out front. Integrating it is pretty straightforward. When we evaluate, we now have the negative limit as t approaches infinity of e to the cosine of t minus e, that minus e happening from putting 0 in place of theta in the expression e to the cosine of theta. But folks, as t approaches infinity, the cosine of t doesn't try to do anything in particular. It oscillates back and forth between 0 and 1, between negative 1 and 1 for all time. Therefore, this integral is divergent. The limit doesn't exist.